what's going on YouTube? Welcome to my math practice stream. Today we are going to be practicing linear algebra again and again every day until we die. I hope y'all are doing well. We just crossed over from a guitar practice stream. I wish that I could keep this little video just hidden like this, you know, just so it's background music, but if I do that, I will forget. So I'm going to keep it up so I don't forget. But yeah, let's do this, y'all. Thank you for watching. Let's practice some linear algebra. First, let's just review what we did yesterday. Yesterday, we practiced vector spaces. And so feel free to pause the video and try to work these examples, these exercises for yourself. Let me know when I make mistakes, because I'm human. It's been 15 years since the last time that I studied math and I got a bachelor's in pure math. I'm having a midlife crisis. I should open videos with that. I'm deep in the throes of a hardcore midlife crisis, and therefore I'm relearning math and trying to become a math teacher now. I worked in software for the last 10 years, and now, I don't know, dude, ChatGPT is taking all the fun out of it. Claude Code, particularly, is just taking all the fun out of it. So let's go back to math. Vector spaces, determine whether F is a vector space. We worked this problem. It took me a little while, and I kind of stumbled on proving some part about it, but to prove that something is a vector space or not a vector space, you need to check these 4 axioms. It's a total mess right now, but it looks nice yesterday. 3.2.7, basic concepts of vector spaces. Is my microphone on? Yeah, okay, it is. Basic concepts of vector spaces. Let F be a vector space of real valued functions. So these are functions that take a real number and return another real number. These are the main functions we think of from high school math, but dude, functions are so much weirder than high school math. But anyways, currently we're looking at regular old high school math functions. And we want to show that the span of these two functions contains all constant functions. So the span is the set of all linear combinations of 2 vectors in general. So I wrote that here. The span of 2 vectors is the set of all combinations. Linear means degree 1, right? There's no squared, like there's no vector squareds or anything like that. Well, if you remember back in trigonometry, 1 is equal to sine squared x plus cosine squared x, so you can multiply both sides by any number k, and then, so k equals k times sine squared x plus cosine squared x, k equals k sine squared x plus k cosine squared x. And then we get a couple of slightly trickier ones. So this problem is essentially asking, express cosine 2x as a combination of sine squared and cosine squared. And this is something called the double angle formula. I can never remember it, so I always derive it every time I need it. But I'm pretty sure it's cosine squared minus sine squared equals cosine 2x. And then essentially write 8 cosine 4x as a combination of 7 and sine squared 2x. That's like a weird one. There's not a special formula for that, but you can figure it out. So pause the video if you want to read my solutions, and let me know, because I didn't refactor these solutions at all. Let me know if you have a much cleaner solution for these. Okay. 3.3.7, coordinatization of vectors. I said that in the last problem, we were expressing something as a combination of 2 vectors. That combination, those numbers, alpha and beta, is the coordinate relative to that basis. So we are finding those coefficients to express this polynomial x cubed plus x squared minus 2x plus 4 as a combination of this ordered basis. So it's in the unusual order. It's not x cubed, x squared, x1, but 1, x squared, x cubed. So this isn't too hard. You just have to rewrite this polynomial in the right order of those, and then that would be the coordinate vector. We end up finding that the coordinate vector is 4, 1, negative 2, 1. And you can pause the video and read my solution if you want to. Then we went to 4.7 or 3.4.7 on linear transformations. C is a space of all continuous functions mapping R to R. This one was tricky for me. I stumbled for a while on this one because I had a hard time remembering the concrete definition of a definite integral from analysis and calculus. I don't think that this book was expecting me to prove this solution. It just said, if possible, give three different functions in the kernel of this linear transformation T. So a linear transformation is a linear function, and in this case, it's a function that takes a function and returns another function. In computer science and programming, we call those higher order functions. A function that takes a function and returns another function. They're wonderful. They're beautiful. So I had a hard time. I saw fairly quickly that the only function in the kernel of T should be 0, but I had a hard time proving that. I had a hard time like that's my intuition. But in math, you don't want to operate on intuition. You want to prove your claims. So I don't think I really came up with a good proof on this. I tried multiple times to try to figure this out, and you can watch the video if you're curious, but I stumbled. I was trying to remember, and I had to look up the concrete definition of the definite integral. So the definite integral, this symbol means this limit. I remember the concept. I remembered it's an infinite Riemann sum, where the rectangles are infinitely thin. And so you have like the function value at some point, some delta x that's tending to 0, and some number of rectangles that goes to infinity. So I was close, but I was like, I'm not going to get this exactly. So I opened up this beautiful book by Tolman and Cohn and found this really nice, clearly stated definition of the definite integral. And so somehow using that, we should be able to prove that if f is in the kernel of T, then f is 0. My attempt was that if we can assume that there is an antiderivative, then the transformation would be this, which would be this, and then f prime of t equals f of t. Ultimately, we get here, from the definition of the definite integral, if you have a antiderivative, and that part is, I'm struggling with my analysis. I don't think that we can assume every function has an antiderivative, but maybe it does. Does it? Does every function have an antiderivative, even if we don't know what it is, even if we can't compute it? This is where I need Leo lectures to show up in the chat and help me out. He did not come to my aid yesterday. I was struggling. So if there is an antiderivative, then, well, we prove that in this case the antiderivative is the constant function. Because f of 1 has to be some value, right? That's just a number. Capital F of 1 is some number, then f of x for every value x always equals that constant number, right? And then from there, the derivative, which is f prime of capital F, like lowercase f is capital F prime. The derivative of a constant function is 0, so then this then f is the 0 function. So I made like some partial progress. If it were the Putnam, which I'm very proud I took and I got some points on, I think I would get 2 points out of 10 with this solution. Or maybe a 7, possibly a 7. It depends on if every continuous function has an antiderivative. I don't know. I don't know if it does. I don't know. I don't know enough. I took analysis, but we didn't quite connect analysis to straight up freshman calculus enough, I feel. Anyways, last problem to summarize last stream is this one about inner products. What is the inner product? It's a abstraction of the dot product. It's the algebraic properties, the axioms of the dot product that make it so dang special. The properties are these 4, P1, P2, P3, P4. We have to have symmetry. The dot product of xy equals the dot product, or the inner product of yx. We have to have the scaling property that R product xy equals product rx y equals product of x and ry. This property turns out to fail for this candidate. We were checking if this is an inner product. And I think that the only... no, it fails 2 things. It also fails the last one. I didn't check it, but we need the inner product of x comma x equals 0 if and only if x is 0. That one would have been easier to prove this thing with, but oh well. Because in this case, 1, 0, 0, inner product with 1, 0, 0 equals x1 plus y1, which is 2. Oh, wait. Oh, shoot, no. What I meant is 1 and negative 1. 1 plus negative 1 equals 0. That's what I meant to say. Then, so, xx equals 0, but x is not 0, and then therefore we fail our important property of the dot product. So, voila, of the inner product. Now I'm struggling because the dot product doesn't satisfy that. The dot product doesn't satisfy that at all. So the inner product is not an abstraction of the dot product. Uh-oh. I've lied to you all many times, but hey, that's why we're practicing. Don't treat these like a course in linear algebra. You're going to learn a lot of wrong things. To do. I must be misremembering something. There must be something that I don't remember correctly. Anyways, this has to be a short stream, so hey, that's good because I'm sick of determinants anyways. I have 10 minutes to do a couple of problems. Let's try to go through a couple of determinant problems as quickly as we possibly can. Fraleigh and Beauregard 416 is a problem about areas, volumes, and cross products. And it asks us to find this determinant. 1, 4, negative 2, 5, 13, 0, 2, negative 1, 3. I want to remind myself, I think that in this section, we don't define... Yep. Wait. We define we have this special formula. So I didn't want to assume that the textbook has already defined certain things, so I wanted to find out what tools are we allowed to use. 1, 4, negative 2, 5, 13, 0, 2, negative 1, 3. We are allowed to use this formula that the determinant of a 3 by 3 matrix A is A1, determinant of B2, B3, C2, C3, minus B1, determinant of, A2, that's what I meant to say, minus A2, B1, B3, C1, C3, plus A3, B1, B2, C1, C2. So this is the formula that we're allowed to use, and the book, I believe, proves this geometrically. And then in the next section, we abstract that to n-dimensional space. So, following that equation, which is proved geometrically, A1 is 1, and then the determinant of the minor matrix is the determinant of, oops, that's not right. I cross out the first row and first column, 13, 0, negative 1, 3, minus 4 times the minor matrix, 5, 0, 2, 3, plus negative 2 times 5, 13, 2, negative 1. 5, 13, 2, negative 1. Well, I'll do the first one. The determinant of a 2 by 2 matrix, we can calculate this geometrically as the area of a parallelogram created by two vectors. We can geometrically calculate this area as AD minus BC. So we're using this special formula. This would be 1 times 13 times 3 minus 0, minus 4 times 5 times 3 minus 0, minus 2 times negative 5 minus 26. Okay, punch that into ChatGPT and you're done. Let's go to 4.2. The determinant of a square matrix. Fraleigh and Beauregard. Are you all entertained? Are you not entertained, everybody? Like, what do you expect when you clicked a video of somebody practicing math on the internet? Dude, what did you expect? in some ways just as boring as it sounds. But in other ways, I think it's actually surprisingly a little interesting to some people. Turns out we can expand by cofactors the same way along any row or column. So this is 5 times the minor matrix 6204. That's 5 times 6 times 4 minus 0. That's 5 times 24, which is who cares. 44.3, let's keep going. Whatever, fine. 120. Fraleigh and Beauregard, 4.3.7. In this section, we start getting some more powerful tools for calculating larger determinants. In particular, we get the tool of row reductions. 0, 0, 2, 0, negative 3, 0, negative 2, 1, 0, 0, 5, negative 3, 2, 0, 0, and negative 3, 4, 0, 0, 0. Again, I mentioned that we can expand by cofactors. Anthropic is solving coding. Their state-of-the-art AI accidentally leaked Claude Code's front-end source code in an NPM commit. Is it only the front-end code? I thought it's everything. I mean, it's not the model weights, right? That's the most important thing. Like, it's not like the training data and everything for the model, which is the important thing. But, yeah, that's interesting. Plus, minus 3 times this 4x4 determinant. I don't know if this is better or worse than just doing row reductions the first time through. Yeah, dude, I think that this is going to be better because it's nearly diagonal. If I interchange two adjacent rows, then we flip the sign of the determinant. I'm going to give the sketch because I got to go. Step 1, interchange. Then the determinant of the new matrix is the negative determinant of the original matrix. Do a few times. And maybe even first. Row 1, 2, 3, 4, 5. New row 5, scale it. So row 5 prime is 5 times the old row 5. Then the determinant would be negative 15. 5 times 4 is 20. 0, 0, 0. We're using a property that you can factor we have the scaling property. So I can factor out, if I quintuple the determinant, then I need to remember to undo that quintupling by multiplying by 1/5. And then likewise, I can do that again, tripling the fourth row. So tripling the fourth row, we have 15, negative 9, 6, 0, 0. Add these two rows together so that row 5 prime is equal to row 5 plus row 4. And then interchange rows using, if you interchange two adjacent rows, then you change the sign of the determinant. And then if you have a determinant of a upper triangular matrix, then that is going to be just the product of the diagonal entries. That's the sketch of this proof, I think, of this exercise. 4.4, I don't have time to write down. I gotta go. Thank you everybody for watching. I gotta go right now. Bye. Bye. Thanks for watching.